Welcome to our comprehensive journey into the fascinating world of physics. Today, we are diving into wave motion, exploring what waves are, how they travel, and the fundamental properties that define them. Let us start with the basics. What exactly is a wave? In physics, a wave is any disturbance from an equilibrium position that travels over time from one region to another. The crucial thing to remember here is that wave motion transfers energy from one point to another, but it does not transfer matter. Think of a ripple in a pond. The water itself just bobs up and down, but the wave's energy travels outward. Broadly speaking, we can classify all waves into two main categories based on how they propagate. These are electromagnetic waves and mechanical waves. Let us break down what makes each of these unique. First, we have mechanical waves. These are produced by the physical disturbance of a material medium. As the wave travels, it is actually the particles of that medium oscillating back and forth that transmit the wave. Because they rely on particles interacting, mechanical waves absolutely require a material medium to travel through. They cannot travel in a vacuum. Often, these are waves we can physically feel or see. You interact with mechanical waves every day. When you speak, you create sound waves, which compress the air molecules around you. Other common examples include water waves crashing on a beach, the physical pulse moving through a compressed spring, or the vibrations on a stretched string, like when you pluck a guitar. On the other hand, we have electromagnetic waves. Instead of vibrating physical particles, these are produced by disturbances of varying electric and magnetic fields. Because they do not rely on physical matter to propagate, they do not require a material medium. This means they can travel perfectly well through the empty vacuum of space. Some common examples of electromagnetic waves include the visible light waves that allow us to see, the high-energy gamma rays emitted by radioactive materials, and the radio waves that transmit music to your car. A very important note to remember is that in a vacuum, all electromagnetic waves travel at the exact same speed, the speed of light, which is 3 × 10⁸ meters per second. Let us summarize the key properties of electromagnetic waves. They can travel in a vacuum, moving at the incredible speed of 300 million meters per second. They consist of oscillating electric and magnetic fields. They typically vibrate with a high frequency, and importantly, they carry no electrical charge. This brings us to the electromagnetic spectrum. As we move from left to right on the spectrum, the wavelength increases, which means the frequency decreases. We start with high-energy gamma rays, move through X-rays and ultraviolet light, into the narrow band of the visible spectrum from violet to red, and then into infrared, microwaves, and finally radio waves, which have the longest wavelengths. To consolidate our understanding, let us compare the two. Mechanical waves need a medium, travel at relatively low speeds, generally have longer wavelengths, and rely on vibrating particles. Electromagnetic waves, however, can travel in a vacuum, move at the extremely high speed of light, typically have shorter wavelengths, and are caused by oscillating electric and magnetic fields. Now that we have classified waves by their medium, let us look at how they actually move. Based on the direction of particle displacement relative to the direction of wave travel, there are two types of wave motion: transverse waves and longitudinal waves. Let us look at transverse waves first. In a transverse wave, the particles of the medium are displaced perpendicularly to the direction the wave is traveling. Imagine shaking a rope up and down. The wave moves forward, but the rope itself just moves up and down. These waves are characterized by their high points and low points. We give specific names to these high and low points. A crest is the part of the wave that rises above the equilibrium line, or the line of zero disturbance. A trough is the part that dips below it. Examples of transverse waves include water waves, waves on a plucked guitar string, and all electromagnetic waves, including light. Next, we have longitudinal waves. In these waves, the particles of the medium are displaced parallel to the direction the wave is traveling. Instead of moving up and down, the particles oscillate back and forth along the same path the wave takes. Because of this, they do not have crests and troughs. Instead, they are characterized by compressions and rarefactions. So, what are compressions and rarefactions? A compression is a region where the particles of the medium are pushed closely together, creating high particle density. A rarefaction is a region where the particles are spread apart, resulting in low particle density. The most common example of a longitudinal wave is a sound wave traveling through the air. To summarize the differences, in transverse waves, particles vibrate at right angles to the wave's travel, creating crests and troughs. In longitudinal waves, particles vibrate along the same axis as the wave's travel, creating alternating regions of compression and rarefaction. How do we visualize these waves in physics? We often use graphs. This first graph is a displacement distance graph. It freezes the wave at a specific moment in time and shows the displacement of all particles along the distance from the source. Here, we can clearly see the crusts, the troughs, the maximum displacement A, and the wavelength, denoted by the Greek letter lambda. Alternatively, we can look at a single particle over time using a displacement time graph. Instead of distance, the x-axis represents time. This shows us how one specific particle bobs up and down as the wave passes it. The distance between two crests here does not represent physical length, but rather the time it takes for one complete cycle, which we call the period, t. Let us formally define the terms we just saw on the graphs. First is amplitude, represented by A. This is the maximum displacement of a particle from its rest or equilibrium position. Next is wavelength, represented by lambda. This is the physical distance between two successive particles that are in exactly the same phase. For example, the distance from one crest to the very next crest. Moving on, an oscillation, or cycle, is one complete back and forth movement of a particle. The period, represented by a capital T, is the time it takes for a particle to complete exactly one of these oscillations. Alternatively, it is the time it takes for the wave to travel a distance of one full wavelength. Period is measured in seconds, and it is the reciprocal of frequency. Frequency, denoted by F, is the number of complete oscillations a wave particle makes in a single second. It is the reciprocal of the period, and its standard unit is the hertz. Next, we have phase. We say two particles are in phase if they are at the exact same point in their vibrational paths and are moving in the exact same direction at the same time. Finally, let us define wavefront, ray, and speed. A wavefront is an imaginary line or surface drawn through an advancing wave connecting all particles that are in phase, like the crest of a ripple in a pond. A ray is simply an arrow showing the direction the wave is advancing. And speed, v, is the linear distance the wave travels divided by the time it takes. We can derive a fundamental equation linking speed, frequency, and wavelength. We know speed is distance over time. If we consider exactly one wave cycle, the distance traveled is one wavelength, lambda, and the time taken is one period, t. So v equals lambda divided by t. Since 1 over t is equal to the frequency, f, we can substitute f into the equation to get the universal wave equation, v equals f times lambda. Let us apply this equation. Example 1. A radio station broadcasts at a frequency of 88.2 MHz. We need to find the wavelength. Remember, radio waves are electromagnetic, so they travel at the speed of light, 3 × 10⁸ meters per second. We convert the frequency to standard hertz by multiplying by 10 to the 6th. Plugging these into v equals f lambda, we divide the speed by the frequency, giving us a wavelength of 3.4 meters. In our second example, a vibrator produces waves that travel 12 meters in 4 seconds with a frequency of 2 Hz. First, we find the speed by dividing the total distance by the total time. 12 divided by 4 gives a speed of 3 meters per second. Now we use our wave equation, v equals f lambda. We plug in our speed of 3 and frequency of 2 and solve for lambda, giving us a wavelength of 1.5 meters. Example 3 involves water waves. A vibrator has a period of 0.02 seconds, and the distance between consecutive crests is 3 centimeters. The distance between consecutive crests is exactly one wavelength, so lambda is 0.03 meters. We find the frequency by taking the reciprocal of the period, 1 divided by 0.02, which is 50 Hz. Multiplying our frequency of 50 by our wavelength of 0.03 gives a wave speed of 1.5 meters per second. Our final example for today has a slight trick. The frequency is 50 Hz, and the distance between 10 successive troughs is 18 centimeters. Be careful here. The distance between 10 successive troughs spans exactly 9 full wavelengths, not 10. So 9 lambda equals 18 centimeters, meaning 1 lambda is 2 centimeters, or 0.02 meters. Multiplying the 50 Hz frequency by the 0.02 meter wavelength gives us a velocity of 1 meter per second. We will build on these calculations as we explore wave properties next. Moving right along with the wave theory of light, let's look at how Huygens' principle applies to reflection at a plane surface. Consider a parallel beam of monochromatic light hitting a flat mirror. If we look at particles A and B on the same incident wavefront at time t, particle B travels to point C in the same time that particle A travels to point D. Because the speed of light is constant in this medium, the distance BC equals AD. We also know that the angles BAD and BCD are 90 degrees, and the hypotenuse BD is common to both triangles. By simple geometry, this proves that the angle of incidence, I, is exactly equal to the angle of reflection, R. Now, let's apply this to refraction at a plane boundary. Imagine a plane wavefront, AB, crossing from air into a denser medium. Let C be the velocity of light in air, and V be its velocity in the medium. If the wave at B takes time t to reach B1, the distance BB1 is c times t. In that same time, the wave at A moves to A1, covering a distance of V times t. If we take the ratio of the sine of the angle of incidence to the sine of the angle of refraction, the geometry of triangles ABB1 and AA1B1 simplifies this to the ratio of distances BB1 over AA1. This leaves us with c times t over v times t, which simplifies to c over v. This ratio of velocities is exactly equal to n, the refractive index of the material. Here is a crucial point to remember about refraction. When light moves from one medium to another, its frequency remains absolutely constant. The wave might slow down and its wavelength might compress, but the number of cycles per second does not change. If we let Fa be the frequency in air and Fb the frequency in the medium, they are equal. Since wave speed equals frequency times wavelength, we can substitute this into our refractive index equation. The frequencies cancel out, leaving us with the refractive index n equal to the wavelength in air divided by the wavelength in the medium. Let's put that equation to work with an example. Suppose the wavelength of a particular beam of light in air is 620 nanometers, and we want to find its wavelength inside a material that has a refractive index of 1.6. We start with our derived formula. The refractive index n equals the wavelength in air divided by the wavelength in the medium. Plugging in our values, we get 1.6 equals 620 divided by lambda. Solving for lambda, we find that the new wavelength is 387.5 nanometers. As expected, the wavelength decreases as the light enters the denser, slower medium. Shifting gears, let's examine the phenomenon of polarization. Because light is a transverse wave, its oscillations happen at right angles to the direction it is traveling. Specifically, these are vibrations of the electric vector. In ordinary unpolarized light, like sunlight or light from a standard bulb, these electric vibrations occur in all possible planes perpendicular to the direction of propagation. We typically represent this in diagrams using a mix of arrows for vibrations parallel to the page and dots for vibrations going in and out of the page. You might wonder if this applies to all waves, like sound. The answer is no. Sound waves cannot be polarized. This is because sound waves are longitudinal, meaning the particles of the medium vibrate back and forth parallel to the direction the wave is traveling. Since there are no perpendicular vibrations to filter or restrict, the concept of polarization simply does not apply to longitudinal waves. When we restrict the electric vibrations of light to just a single plane, we create plane polarized light. In diagrams, this is shown as a ray with only one set of markers, either just the arrows or just the dots, indicating that all other planes of vibration have been blocked. It is also possible to have partially polarized light, where vibrations in one plane are significantly stronger than the others, but the light isn't perfectly restricted to a single plane. How do we actually produce polarized light? One common method is by reflection. When ordinary unpolarized light strikes a boundary between two media, like air and glass, part of it is reflected and part is transmitted, or refracted. Interestingly, at one specific angle of incidence, known as the polarizing angle, the reflected ray becomes completely plane polarized. The vibrations in this reflected ray are entirely parallel to the reflecting surface. Furthermore, at this specific angle, the reflected ray and the refracted ray are exactly perpendicular to each other. We can express this relationship mathematically using Brewster's law. Starting with Snell's law, the refractive index of air times the sine of the angle of incidence equals the refractive index of glass times the sine of the angle of refraction. Because the reflected and refracted rays are 90 degrees apart, the angle of refraction r equals 90 minus the angle of reflection. By the law of reflection, the angle of incidence equals the angle of reflection, which we'll call theta. Substituting this in, we get sine theta equals the refractive index of glass times the sine of 90 minus theta, which is cosine theta. Dividing sine by cosine gives us tangent, so the refractive index of the material simply equals the tangent of the polarizing angle. Let's look at a quick example of Brewster's law. Suppose the polarizing angle for light hitting a glass plate in air is measured to be 56.5 degrees. We want to find the refractive index of this glass. Using our newly derived formula, we know that the refractive index of the glass, Ng, is equal to the tangent of the polarizing angle, theta p. We simply calculate the tangent of 56.5 degrees. This gives us a refractive index of approximately 1.51. Here's another scenario. This time, we know the transparent medium has a refractive index of 1.62, and we want to find both the angle of incidence that produces plane polarized reflected light and the resulting angle of refraction. First, we use Brewster's law. Theta equals the inverse tangent of 1.62. This gives us a polarizing angle, or angle of incidence, of 58.3 degrees. To find the angle of refraction, we remember that at this specific incidence, the reflected and refracted rays are 90 degrees apart, so we subtract 58.3 from 90, giving us an angle of refraction of 31.7 degrees. Now it is your turn to try one. If the polarizing angle for light and air incident on a glass plate is 57.5 degrees, what is the refractive index of the glass? You can use the exact same steps we just covered. Take a moment to calculate it. If you use the tangent function on 57.5 degrees, you should arrive at a refractive index of 1.57. Another way to produce polarized light is through scattering. When unpolarized light from the sun travels through the atmosphere, it strikes air molecules and scatters. The light that continues straight through remains unpolarized. However, if you look at the light that is scattered at exactly a 90-degree angle to the original incident ray, that light is completely plane polarized. This is why the sky appears partially polarized when viewed through a polarizing filter at certain angles from the sun. A third method is double refraction, often demonstrated using a special crystal setup called a nickel prism. When a narrow beam of ordinary light enters the prism, it splits. If we look at the emergent light through a second polarizing filter, called an analyzer, we can test its polarization. By gradually increasing the angle of incidence and rotating the analyzer, we will find a specific point where the light is completely cut off, turning completely dark. This proves that the light emerging from the prism at that angle is completely plane polarized. Polarization has several highly practical applications. One fascinating use is measuring the concentration of sugar in a solution. The apparatus uses a polarizer to create polarized light, which then passes through a tube. First, we calibrate the system empty by rotating an analyzer until the light is completely blocked. Then, we fill the tube with the sugar solution. Sugar molecules are optically active, meaning they actually twist the plane of polarization as the light passes through. Because the plane has rotated, light suddenly passes through the analyzer again. By measuring exactly how many degrees we have to rotate the analyzer to block the light a second time, we can calculate the exact concentration of the sugar. You're probably most familiar with polarization in sunglasses. When sunlight reflects off horizontal surfaces like water or a road, it becomes partially polarized horizontally, creating harsh glare. Polarized sunglasses have a vertical chemical coating that blocks this horizontally polarized reflected light, drastically reducing glare. Beyond eyewear, polarization is essential in creating 3D holograms, analyzing mechanical stress in transparent plastics through a technique called photoelasticity, and it is the fundamental technology that allows liquid crystal displays, or LCD screens, to function. Let's transition now to another major wave phenomenon, interference. Interference occurs when waves from two coherent sources overlap, or superpose, in the same space. This overlapping creates a distinct pattern of alternating maximum and minimum intensity. When the waves arrive out of phase, specifically when their path difference is an odd multiple of half a wavelength, they cancel each other out, creating a region of minimum intensity or darkness. Conversely, when the path difference is an exact whole number multiple of a full wavelength, the peaks align, reinforcing each other to create a region of maximum intensity or brightness. To get a stable, observable interference pattern, the two wave sources must be coherent. What does that mean? Coherent sources must meet strict criteria. They must emit waves of exactly the same frequency, they should have nearly the same amplitude for the best contrast, and most importantly, they must maintain a constant phase difference over time. If the phase difference randomly fluctuates, the interference pattern will shift too rapidly to be seen, which is why two separate light bulbs won't produce an interference pattern, but a single laser split into two beams will. We will explore exactly how to calculate these interference patterns next. Picking up right where we left off, let us examine the specific conditions required for observable interference to take place. For interference patterns to be clearly visible, the two wave trains must have nearly equal amplitudes. Furthermore, there must be a constant phase relationship between them, meaning the sources must be coherent. Physically, these coherent sources need to be positioned close to each other, while the screen where the pattern is observed should be placed as far away as possible to magnify the fringe separation. There are two main types of interference. The first is constructive interference. This occurs when the intensities of two coherent sources reinforce each other, resulting in a maximum intensity at the point of superposition. Visually, you can think of this taking place when the crest of one wave perfectly aligns with the crest of another, and similarly, their troughs align. Because the displacements are in the same direction, they add together, resulting in a much larger resultant amplitude. Conversely, we have destructive interference. This is the exact opposite effect, where the intensities of the two coherent sources cancel each other out, yielding a minimum intensity. This cancellation happens when the crest of one wave meets the trough of another wave. Because their displacements are in opposite directions, they subtract from one another, resulting in a very small or sometimes completely zero resultant amplitude. To determine whether constructive or destructive interference occurs at a specific point, we look at the path difference. This is simply the difference in the distance traveled by the two waves from their respective sources to the point of overlap. Let us call it point P. If the path difference is 0 or a whole number multiple of the wavelength, the waves arrive in phase, creating a bright band of constructive interference. If the path difference is an odd multiple of half a wavelength, they arrive out of phase, creating a dark band of destructive interference. Now, let us introduce the concept of the optical path. The optical path is defined as the length in a vacuum that would contain the exact same number of waves as a given length in a specific medium. Mathematically, it is the product of the geometrical path length and the refractive index of the medium. If light travels a distance d in air, the optical path is simply d, since air's refractive index is essentially 1. However, if we insert a transparent slab of thickness t and refractive index n, the new optical path becomes d plus the quantity n minus 1 times t. Closely related to path difference is phase difference, which measures the difference in the phase angles of two waves at any given moment. We can calculate the phase difference, denoted by phi, by multiplying 2 pi over lambda by the optical path difference. When waves are perfectly in phase, meaning their crests meet, the phase difference is 0, leading to constructive interference. When they are completely out of phase, meaning a crest meets a trough, the phase difference is pi radians, leading to destructive interference. How do we actually create these coherent sources in a lab? One method is by the division of a wavefront. Using a double-slit setup, light from a single monochromatic source passes through a narrow single slit, diffracting outward. This single wavefront then strikes two parallel narrow slits, S1 and S2. Because the light emerging from S1 and S2 originates from that exact same initial wavefront, the two new wave trains maintain a constant phase relationship, making them perfectly coherent sources ready to interfere. Another way to divide a wavefront is by using a Fresnel biprism. Here, a biprism with a very large angle is placed in front of a narrow monochromatic light source. As the light passes through the upper and lower halves of the prism, it refracts, appearing to originate from two distinct virtual sources, S1 and S2. Just like the double slit, these virtual sources are coherent because they come from the same original wavefront. This biprism method is often preferred in experiments because it converges more light onto the screen, producing significantly brighter fringes. The second major method for producing coherent sources is by the division of amplitude. This happens through successive reflections. The simplest example is when light strikes a boundary between two different media, like air and glass. At the point of incidence, the light's energy is split. Part of it is reflected back into the air, and part is transmitted into the denser glass. Because the total intensity is divided, and intensity is proportional to the square of the amplitude, we effectively divide the wave's amplitude into two coherent parts. We can utilize this division of amplitude in an air wedge setup. Imagine two glass plates resting on each other, slightly separated at one end to form a thin wedge of air. When monochromatic light shines down almost normally, it hits the air film. Some light reflects off the top boundary of the air film, while the rest transmits through and reflects off the bottom boundary. These two reflected rays originate from the same initial wave, so they are coherent. When they travel back up and overlap, they create an interference pattern. This brings us to the classic Young's double slit experiment. When a wavefront from a single source hits the double slits, S1 and S2, it divides, turning them into coherent sources. The waves spread out and superimpose on the screen. Where crests meet crests, we get bright fringes, and where crests meet troughs, we get dark fringes. This creates a beautiful series of equally spaced, alternating parallel bands. Exactly at the center point, P, the waves from both slits travel the exact same distance. They arrive perfectly in phase, guaranteeing a bright central fringe. There are several important experimental observations to note about this setup. First, if you cover one of the double slits, the interference pattern completely vanishes because you no longer have two overlapping wave trains. Second, if you move the primary monochromatic light source closer to the slits, the overall intensity of the light passing through increases. This does not change the spacing of the fringes, but it does make the bright bands significantly brighter and easier to see. What happens if we adjust the internal distances of the apparatus? If we reduce the distance between the single slits and the double slits, the fringe separation on the screen remains unchanged, but again, the bands become brighter due to the higher intensity of light reaching the double slits. However, the distance between the two slits themselves is critical. If we reduce the double slit separation, the fringes on the screen spread further apart. Conversely, widening the gap between the slits packs the fringes closer together, eventually blurring them out entirely. Most of our calculations assume monochromatic or single-color light, but what if we use standard white light? Because white light is a spectrum of different wavelengths, each wavelength creates its own interference pattern. At the exact center, all wavelengths travel the same distance and interfere constructively, so the central fringe remains white. On either side, however, the patterns separate. Because blue light has a shorter wavelength, its first bright fringe appears closest to the center, while the longer wavelength red fringes appear further out, creating a rainbow effect. The width of the initial single slit is also crucial. If we widen this single slit, the distinct interference fringes will gradually disappear. Why? Because a wide slit effectively acts as a large collection of many narrow slits placed side by side. Each of these tiny sections of the wide slit produces its own independent interference pattern on the screen, slightly shifted from its neighbor. When all these countless shifted patterns overlap, the bright and dark spots wash each other out, leaving only a uniform, featureless illumination on the screen. Let us look closer at the separation between the double slits, denoted as A. When the separation is much larger than the wavelength, we just see bright bands, roughly the size of the slits, like simple shadows. As we narrow the separation so it is close to the wavelength of the light, a distinct diffraction pattern emerges, featuring a central band flanked by colored fringes. If we narrow it even further, so A is less than the wavelength, the central bright band widens dramatically, spreading well into the geometrical shadow. And of course, completely, no light passes at all. Now, let us derive the mathematical formula for the distance between these fringes. Consider two slits, A and B, separated by a distance A, projecting onto a screen a distance d away. Waves from A and B meet at point P, which is a distance yn from the center. By dropping a perpendicular from A to the lower ray, we find the path difference is the segment BN, which equals A sine theta. Because the screen is far away, theta is tiny, allowing us to approximate sine theta as tangent theta. Looking at the large triangle, tangent theta is yn over d. Substituting this in, our path difference Bn equals A times yn over d. Let us apply this to find the spacing of the bright fringes. For constructive interference to form the nth bright fringe at point P, the path difference Bn must equal an integer multiple of the wavelength, n lambda. Equating our two expressions for Bn, we get A times yn over d equals n lambda. Solving for yn gives us the position of the nth bright fringe. To find the distance between adjacent fringes, we simply subtract the position of the nth fringe from the n plus 1 fringe. The n terms cancel out, leaving us with the beautiful, simple formula, fringe separation y equals lambda times d divided by A. We can perform the exact same derivation for the dark fringes. The only difference is the condition for destructive interference. The path difference Bn must equal an odd multiple of half a wavelength, or n plus 1/2 lambda. We set this equal to A times yn over d and solve for the position yn. When we calculate the separation between two adjacent dark fringes by subtracting yn from yn plus 1, the fractional terms perfectly cancel out. We arrive at the exact same formula. The separation between dark fringes is also lambda times d over A. The fringes are equally spaced. Let us put this formula into practice with an example. Suppose we observe 21 bright fringes spanning a total distance of 3.6 millimeters. The screen is 29 centimeters away, and our light has a wavelength of 5.5 times 10 to the negative 7 meters. We need to find the slit separation, A. First, we find the individual fringe separation, y, by dividing the total distance by the number of fringes, giving us 0.171 millimeters. Next, we rearrange our formula to solve for A, which is lambda times d over y. Plugging in our values, making sure to convert centimeters and millimeters to standard meters, we calculate a slit separation of 9.327 times 10 to the negative 4 meters. In our second example, we are given the slit separation as 0.28 millimeters and a screen distance of 4 meters. We are told the distance from the central fringe to the fourth bright fringe is 1.2 centimeters, and we need to find the wavelength. We know the position of the nth fringe is n times lambda times d over a. The distance from the center to the fourth fringe is simply y4 minus y0, which simplifies to 4 times lambda times d over a. We set this equal to our given distance of 1.2 times 10 to the negative 2 meters. Rearranging to solve for lambda, we find the wavelength is 2.1 times 10 to the negative 7 meters. Let us try another variation. Here, the sixth bright fringe is located 4 millimeters away from the center of the pattern. The wavelength is 6.0 times 10 to the negative 7 meters, and the screen is 60 centimeters away. We need to calculate the slit separation, A. Following the same logic as before, the distance to the sixth fringe is 6 times lambda times d over a. We plug in 4 times 10 to the negative 3 meters for the distance and 0.6 meters for the screen distance. Solving for a yields a slit separation of 5.4 times 10 to the negative 4 meters. Example 4 is structurally identical to the last one, just to reinforce the concept. This time it is the eighth bright fringe, located 5 millimeters from the center. The wavelength is 6.2 times 10 to the negative 7 meters, and the screen is 80 centimeters away. We set up our equation. The distance y equals 8 times lambda times d over a. Substituting our known values, 5 millimeters for y and 0.8 meters for d, we isolate a. The calculation gives us a slit separation of 7.94 times 10 to the negative 4 meters. What if we need to find the distance between two specific fringes, rather than from the center? In this example, we want the distance between the fourth and second bright fringes. We have a slit separation of 0.2 millimeters, a screen distance of 1 meter, and a wavelength of 550 nanometers. We find the distance by subtracting the position of the second fringe from the fourth fringe. This simplifies neatly to 2 times lambda times d over a. Plugging in our values and remembering to convert nanometers to 10 to the negative 9th meters, we get a distance of 5.5 millimeters. This final double slit example tests our understanding of proportionalities. We start with a fringe separation of 1 millimeter. Then we change 3 parameters. We double the screen distance, half the slit separation, and change the wavelength from 650 to 400 nanometers. We set up 2 equations, one for case 1 and one for case 2. By dividing the equation for case 2 by the equation for case 1, the unknown variables d and a cancel out entirely. We are left with a ratio of the new parameters over the old parameters, allowing us to solve directly for the new fringe separation. Here are 3 practice exercises for you to test your understanding of the Young's double slit formulas. The first asks you to find the slit separation given the position of the fifth bright fringe. The second requires calculating the distance between 2 specific fringes, the sixth and the second. The third asks you to work backward to find the wavelength of the light source given the position of the 10th bright fringe. The answers are provided in brackets so you can check your work after setting up the equations. We can use the Young's double slit setup as a practical experiment to measure the exact wavelength of a light source. We arrange the apparatus with a monochromatic source, single slit, and double slits. We place a viewing microscope at a measured distance d from the slits. Looking through the microscope, we count the number of bright fringes within a fixed length on a scale to accurately determine the fringe separation, y. We measure d with a standard meter rule and carefully measure the tiny slit separation a using a specialized traveling microscope. Finally, we calculate the wavelength using our rearranged formula, lambda equals y times a divided by d. We can adapt this exact same experiment to compare the wavelengths of different colors of light. Instead of a monochromatic source, we use a white light source and place a red-colored filter in front of the slit. We measure the fringe separation for the red light, calling it YR. Then we swap the red filter for a blue one and repeat the process to find YB. When we compare the results, we will consistently find that the fringe separation for red light is greater than that for blue light. Because wavelength is directly proportional to fringe separation, this proves experimentally that red light has a longer wavelength than blue light. Moving on from double slits, let us explore interference in thin films, specifically using an air wedge. Imagine 2 flat glass plates touching at one end and slightly separated at the other, forming a wedge-shaped film of air between them. When monochromatic light shines down, it hits this air gap. Some light reflects off the bottom surface of the top glass plate, while some travels through the air gap and reflects off the top surface of the bottom plate. These two reflected rays are coherent. As they travel back upward and overlap, they interfere, creating a pattern of straight, parallel fringes. If we used white light here, we would see beautiful colored bands instead. Let us derive the fringe separation for this air wedge. For dark fringes, the path difference, which is roughly twice the thickness of the air film, 2t, must equal n lambda. For the next adjacent dark fringe, 2tn plus 1 equals n plus 1 lambda. Subtracting these, we find the difference in thickness between adjacent fringes is lambda over 2. Looking at the geometry of the wedge, the tangent of the wedge angle theta equals the change in thickness divided by the horizontal fringe separation, y. Substituting our thickness difference, we get tan theta equals lambda over 2y. Since the angle is incredibly small, tan theta is approximately just theta in radians, giving us the final formula, fringe separation y equals lambda over 2 theta. Just like with the double slit, the derivation for bright fringes in an air wedge yields the exact same result for fringe separation. We start with the condition for constructive interference in this specific setup, where the path difference, 2t, equals n minus 1/2 lambda. When we set up the equation for the n plus 1 fringe and subtract the 2, the fractional halves cancel out perfectly. We are once again left with the difference in thickness equaling lambda over 2. Following the exact same geometric steps with the tangent of theta, we arrive at the identical formula. The separation between bright fringes, y, is lambda over 2 theta. Let us look at an example calculation for an air wedge. Two glass slides are propped open by a wire to form the wedge. Using light with a wavelength of 5.6 times 10 to the negative 7 meters, we observe 20 fringes occupying a space of 15 millimeters. We need to find the angle of the wedge. First, we find the individual fringe separation, y, by dividing 15 millimeters by 20, giving 0.75 millimeters. We use our formula, tan theta equals lambda over 2y. Plugging in our values and taking the inverse tangent, we find the wedge angle is an incredibly small 0.021 degrees. In this second example, we want to find the total number of dark fringes visible across the entire wedge. The slides are separated at the far end by a wire with a diameter of 0.04 millimeters. This diameter represents the maximum thickness, T, of our air film. The wavelength is 5 times 10 to the negative 7 meters. We use the path difference condition for dark fringes, 2t equals n lambda. We rearrange to solve for n, the number of fringes, which equals 2t over lambda. Plugging in the maximum thickness and the wavelength, we calculate that exactly 160 dark fringes will be formed. Here is a highly practical application, using interference to measure the thickness of a very thin object, like a sheet of paper. The paper is placed 16 centimeters from the line of contact, creating the wedge. The light wavelength is 5.8 times 10 to the negative 7 meters, and the resulting fringe separation is 2.0 millimeters. We know tan theta equals lambda over 2y, but geometrically, it also equals the opposite side, the paper thickness t, over the adjacent side, the 16 centimeter length. By equating these two expressions for tan theta, we can solve directly for t. The calculation reveals the paper is 2.32 times 10 to the negative 5 meters thick. Example 4 is identical in concept to the previous one, this time measuring a piece of metal foil. The foil is placed 12.5 centimeters from the contact line. The wavelength is 5.4 times 10 to the negative 7 meters, and the observed fringe separation is 1.5 millimeters. We set up the exact same geometric relationship. Lambda over 2y equals the thickness t over the length of the wedge. Rearranging and plugging in the numbers, we calculate the thickness of the metal foil to be 2.25 times 10 to the negative 5 meters. Let us combine these concepts into one comprehensive problem. We have 12 centimeter slides separated by a wire with a diameter of 2.5 times 10 to the negative 3 centimeters, using 500 nanometer light. First, to find the fringe separation, we equate lambda over 2y to thickness over length and solve for y, getting 1.2 millimeters. Second, to find the total number of dark fringes, we use the formula 2t over lambda, which gives us exactly 100 dark fringes. Finally, for the bright fringes, we use the condition 2t equals n minus 1/2 lambda. Solving for n gives us 100.5, which means 100 full bright fringes fit within the wedge. Here are two practice exercises for thin film interference. The first is a straightforward calculation to find the thickness of a metal foil acting as a wedge spacer, given the fringe separation and wedge length. The second exercise is a two-part question. First, it asks you to conceptually explain how the fringes are formed in the air wedge. Remember to discuss the partial reflection at the top and bottom boundaries of the air film. Then it asks you to calculate the diameter of the wire spacer, given that 10 dark fringes occupy a specific distance.
You might wonder why we only talk about thin films. Why do we not see interference fringes in a thick block of glass or a wide air gap? Bright fringes occur when the path difference matches a specific multiple of the wavelength. In a thick film, the path difference is very large. Because of this large difference, many different wavelengths, meaning many different colors of light, will satisfy the condition for a bright fringe at the exact same location. When all these different colors overlap at the same spot, they recombine to form uniform white light, completely blurring out any distinct interference pattern. Another famous example of thin film interference is Newton's rings. Instead of two flat plates, this setup places a convex lens with a very long focal length on top of a perfectly flat glass plate. This creates an air wedge that is circularly symmetric, with the thickness increasing outward from the center point of contact. When monochromatic light shines down, it reflects off the boundaries of this curved air film. Because the film's thickness is constant along any given radius, the resulting interference pattern forms a series of beautiful concentric dark and bright rings, with a dark spot right at the center where the glass touches. You have likely seen thin film interference in everyday life, such as the swirling rainbow colors on a puddle of water with a thin layer of oil on top. When sunlight hits the oil film, some light reflects off the top surface, while some refracts into the oil and reflects off the bottom oil-water boundary. When these two sets of light waves travel back to your eye, they interfere. Because white sunlight contains all colors, the specific thickness of the oil at any given point will cause constructive interference for one specific color and destructive interference for others. As the thickness varies, or as you change your viewing angle, the colors you see shift and change. Beyond beautiful colors, interference has highly practical applications in industry and science. One major application is testing the absolute flatness of optical surfaces. By placing a newly manufactured glass surface against a perfectly flat standard reference plate, an air wedge is formed. If the new surface is perfectly flat, the interference fringes will be perfectly straight and equally spaced. Any microscopic bumps or dips will cause the fringes to warp and distort, instantly revealing the flaw. Another critical application is the blooming of lenses, where thin films are applied to camera and telescope lenses to create destructive interference for reflected light, thereby reducing glare and increasing transmission. We will explore more optical phenomena in the next section. Let's explore the diffraction of light. Diffraction is the spreading of waves beyond geometrical boundaries, which leads to interference. To study this, we use a diffraction grating, which is a transparent plate featuring many equidistant small parallel lines, typically drawn using a diamond pencil. When a monochromatic wavefront hits a transmission grating, the light passes through narrow slits whose widths are comparable to the light's wavelength. The light diffracts, or spreads out, through these spaces into the region beyond the grating, where the waves overlap and superpose. As these diffracted waves superpose, they create an interference pattern. If the path difference between waves from consecutive slits is an exact multiple of a full wavelength, they interfere constructively, forming a bright band. If the path difference is an odd multiple of half a wavelength, they interfere destructively, creating a dark band. This entire process of spreading and interfering is the essence of diffraction. What happens if we increase the number of narrow slits in our grating? The intensity of the principal maxima increases, while the subsidiary maxima become fainter. This happens because the interference of the principal maxima is always perfectly constructive, pooling more light together, whereas the subsidiary maxima experience more destructive interference from the additional slits. There are two main types of diffraction gratings. A standard transmission grating has lines ruled on glass, so the spaces between the lines transmit the light through. In contrast, a reflection grating has lines ruled on polished metal, meaning the spaces reflect the light to form the diffraction pattern. To find where the bright bands, or maxima, occur, we look at the path difference between adjacent slits. For a grating with spacing d, the path difference is d sine theta. For a maximum, this must equal an integer number of wavelengths, n lambda. This gives us the fundamental grating equation, d sine theta equals n lambda. Let's apply this to an example. We have sodium light of 589 nanometers hitting a grating with 600 lines per millimeter. We need the angle for the first order maximum. First, we find the slit spacing d by taking the reciprocal of the lines per meter. Plugging d, n equals 1, and the wavelength into our equation, we solve for theta and get 20.70 degrees. In our second example, we know the wavelength is 600 nanometers, the order n is 2, and the angle is 30 degrees. We need to find the number of lines per centimeter. By rearranging our formula to solve for 1 over d, we plug in our values to find 4.17 times 10 to the fifth lines per meter, which converts to 4,170 lines per centimeter. Here, a 600 lines per millimeter grating gives a first-order maximum at 20 degrees. First, we solve for wavelength, getting 5.7 times 10 to the negative 7 meters. To find the maximum number of observable orders, we set sine theta to its maximum value of 1. Solving for n gives 2.92. Since n must be an integer, the highest observable order is 2. In this example, we find the total number of images. Using a 500 lines per millimeter grating and 526 nanometer light, setting sine theta to 1 gives an n of 3.8. The maximum order is 3. Remember, we see these 3 orders on both sides of the central 0-order image, so 3 plus the central one gives a total of 7 images seen. Diffraction has several practical applications. It is widely used to precisely measure the wavelength of light. It is also essential in spectrographic studies to analyze the composition of light sources, and it plays a key role in the creation of holograms, which are 3-dimensional photographs. To measure the wavelength of light, we use a spectrometer setup. We adjust the telescope to focus parallel light and the collimator to produce a parallel beam from our monochromatic source. The diffraction grating is placed on the level table so that its plane is perfectly perpendicular to the incident light. Next, we locate the central 0-order image and note its position. We then rotate the telescope to one side until we find the first-order image and record angle theta 1. We restore the telescope and rotate it to the opposite side to find the other first-order image, recording angle theta 2. Finally, we calculate the wavelength using the average of these two angles in our grating equation. For diffraction to be observable, the size of the obstacle must be roughly the same order of magnitude as the light's wavelength. When comparing spectra, a prism produces a single, less pure spectrum where shorter wavelengths spend the most. A diffraction grating produces multiple, highly pure spectra, and it deviates longer wavelengths the most. Here are some practice exercises to test your understanding. The first asks you to find the grating spacing, given the wavelength and the second-order angle. The second requires you to find the wavelength and the maximum number of observable orders, given the grating spacing and the first-order angle. Try working through these using the formulas we discussed. Let's review the UENB 2016 past paper questions. You are asked to define diffraction and use Huygens principle to explain the single slit pattern. There is a calculation to determine the highest order of diffraction for a given wavelength and grating. Finally, the paper tests your knowledge of polarization, asking for definitions, calculations involving refractive index, and methods of producing polarized light by reflection. In the 2015 paper, the focus includes defining wave terms like phase difference and optical path difference. You need to explain fringe formation in an air wedge and calculate the wedge angle. There is also a standard Young's double slit calculation to find slit separation, and a descriptive question on producing polarized light via double refraction. The 2013 paper asks for a detailed explanation of fringe formation by transmission gratings and a full description of the spectrometer experiment to measure wavelength, which we just covered. It also asks you to explain the real-world phenomenon of colored oil layers on water due to thin film interference, and to define and apply plane polarized light. For 2012, questions probe why sound, a longitudinal wave, cannot be polarized unlike light. You must predict observations when rotating a Polaroid sheet and calculate the sun's elevation for complete polarization using Brewster's angle. The paper again asks for the spectrometer experiment description and includes a calculation for the number of diffraction images and their angles. The 2011 exam requires distinguishing between unpolarized and polarized light. It asks how a biprism creates coherent sources and why thick films do not show interference effects. You also have a Young's double slit calculation and a conceptual question on how increasing the number of slits in a grating affects the intensity of the fringes. In 2010, foundational definitions of diffraction and polarization are tested. You must calculate angles of incidence and refraction for polarization. A unique calculation asks for the grating spacing given the angular separation of two closely spaced sodium lines. Finally, you must state the differences between spectra produced by prisms and gratings. The 2008 paper starts by distinguishing constructive and destructive interference. It heavily features the air wedge, asking for explanations of fringe formation with both monochromatic and white light, followed by a calculation to find the thickness of the paper creating the wedge.
It concludes with questions on producing and using polarized light. For 2007, you need to state Huygens' principle and use it to derive the speed of light in a dielectric, followed by a wavelength calculation. The paper tests the core definitions and conditions for wave interference and path difference. It also includes an air wedge calculation to find the total number of observable fringes. The 2006 exam covers the superposition principle and optical path. It asks you to explain thin film interference in oil. A major question involves a Young's double slit setup, asking you to predict what happens to the fringes if you cover a slit, widen the source, or change the slit separation and screen distance. It ends with a standard grading calculation. Finally, the 2004 paper requires you to sketch the electric and magnetic vectors of a polarized light wave. You must define coherent sources and derive the formula for fringe width in a double slit experiment, followed by a calculation. The paper concludes with defining diffraction and calculating the angle for a first-order image. Moving to Section C, we introduce electromagnetism and AC circuits. A magnet is a substance that attracts magnetic materials and aligns south-north when freely suspended. Materials are categorized based on this. Ferromagnetic substances, like iron and cobalt, are attracted to magnets. Non-magnetic substances, like rubber and glass, are not. This leads us into studying the specific properties of magnets. Let's wrap up our final key takeaways. We've seen how diffraction gratings use multiple slits to create precise interference patterns. The grating equation is your primary tool for calculating maxima angles, wavelengths, and slit spacing. Remember that gratings produce purer spectra than prisms. We also reviewed extensive past paper questions, highlighting the importance of mastering interference and polarization. Finally, we briefly introduced magnetic materials, setting up your next major topic,